central limit theorem. Central limit theorem says a sampling distribution of means becomes normal as n increases regardless of the shape of the original distribution. So whatever the raw data is, if you take the mean and look at the sampling distribution of the mean, doesn't matter what the shape of the original distribution is. As n increases, the sampling distribution will become normal. So binomial is going to become normal, and it applies to other statistics. So for example, the variance, as you increase your sample size, the variance becomes an increasingly normal distribution. So the reason this is important or matters is because, when we look at our statistics like analysis of variance and regression and so forth, the tests probability values depend on the normal distribution. And so even if the data aren't normally distributed, if we have a lot of them, then the test statistics are going to be normally distributed. Like the means, for example, are going to be normally distributed, and we want to test inferences about the means, and so we can use the normal to do those tests, even if the raw data are nasty. Properties of the normal. So if parent distribution is normal, so the raw data are normal, the sampling distribution of the mean is going to be normal regardless of the sample size, regardless of n. If a distribution is normal, then the sampling distribution of the mean and the sampling distribution of the variance are independent. So the mean and the variance are completely disconnected. So if you know one, you don't know the other. As I mentioned before, that isn't true for other distributions, like, for example, the percentage. And that turns out to be a really nice thing. For statisticians, you can derive stuff about the mean, and you don't have to worry about the variance, or vice versa. Okay, so now the previous example of a confidence interval that I gave you, we didn't make any assumption about the distribution of the data. But now we're going to assume that the data are normally distributed. So over samples of size n, the probability is 0.954 minus 1.96 times the standard error of the mean. And that's good for the difference between the sample mean and the population mean. So we can go up and down 1.96 standard errors. For the sample values of the mean, the probability is 0.95, that the sample mean minus 1.96 standard errors is less than or equal to mu. The population value is less than or equal to the sample mean plus 1.96 standard errors. So these two formulas really say the same thing. So what this means is population mean is likely to be within 2 standard errors of the sample mean. So you have a sample mean and you go up and down 2 standard errors. And remember, the standard error is the standard deviation divided by the square root of n. Then you're pretty likely to know where the population value is. And this is really cool because we can be pretty sure about our result, and we can communicate precisely our uncertainty about our result, and we don't have to know the actual population value, which is just kind of amazing. It comes from statistics. So we can use the normal to create a confidence interval of any size. So 0.95 is conventional, but we can have 0.99, we can 0.85. There are some places where 0.90 is the convention, but mostly it's 0.95. That's mostly what people do. Size of the confidence interval depends on the desired certainty. So if we want 95 versus 99%, and the size of the standard error. So this 95 versus 99, that's going to give us a value of z from the normal, and the standard error of the mean is going to depend on the standard deviation of the raw data and the sample size, n. Typically, it's much easier to control the sample size, n, than the standard deviation in the population, sigma. If you're interested in the height of people, there really isn't much that you can do about the standard deviation in the population. And if you want that smaller, you could say, well, I don't want all people, I just want men or women or school children or something. Then you're going to have less variability there. But mostly that's sort of fixed by the population itself. I want to know about adults in the United States. Well, there's nothing I can do about the sigma. It is what it is. But I can say something about the sample size. Suppose that my standard deviation is 10. If I have 25 people, then the standard error of the mean is 2. So it's 10 divided by the square root of 25, or 10 over 5, which is 2. Confidence interval width is about 8. So we're going to go up and down 2 standard errors, right? So 2 times 2 is 4. So we go down 4, and 2 times 2 is 4. We go up 4, and that gives us a range of about 8. That width is about 8. If we have 100 people, then square root of n is 10, and 10 over 10 is 1. Standard error of the mean is 1. Confidence interval width is about 4. So we really shrank it quite a bit, from 8 to 4. And so we did that by increasing our sample size. So as n gets large, we're going to get a smaller and smaller confidence interval, but you need more and more people to get the same amount of decrease, because it's the square root of n. So it's not sigma over n, it's sigma over the square root of n. So from 25 to 100, you get, pretty good decrease. But if you go up 125, you're not going to get nearly as much bang for the buck. Okay, so it's time to ask yourself what the central limit theorem is. What does it say? What does it mean? Why is the number 1.96 such a big deal? And assume that scores on a curiosity scale are normally distributed. Sample mean is 50 based on 100 people. Population standard deviation is 10. Find an approximate 99% confidence interval for the population mean. Central limit theorem says that as the sample size increases, the sampling distribution of the statistic becomes normally distributed. So regardless of the shape of the raw distribution, could be flat like the dice, could be some kind of nasty skewed thing like housing prices or something like that. Doesn't matter. As the sample size increases, the sampling distribution of the mean is going to become normally distributed. Why is the number of 1.96 such a big deal? Well, because from the normal distribution, if you go up and down 1.96, that gives you 95% of the normal distribution when you've got z-scores. When you have the unit normal with 0 and 1 as the mean and the standard deviation, then 1.96 gets you plus and minus 1.96 gives you 95% of that normal distribution. And we can use that 1.96 and scale it by a standard error for any mean to find the 95% of some distribution. Assuming that scores are on a curiosity scale are normally distributed. Our sample mean is 50. Population standard deviation is 10. Okay, so what's the standard error? Well, that will be 10 divided by 10 is 1, and approximate 99%. So 1.96 for a 95%. So if we go up and down 2, that would be 48 to 52. But we want 99%. So let's just say that we're going to go up and down 3, because we want to be conservative now. So it's 99%. We want to be really sure that the mean is in there. Well, if we go up and down 3, that would be 47 to 53. If you look up the critical value for Z, you can find the correct number for a 99% confidence interval. Good for you.